Thanks a lot. Thanks for the organizers. I'm very pleased to be there. So I'm very old friend. So I know Stefan for 30 years old. So I think this photo was during his military service or something like around 82. So much before wavelets, and of course we remain friends. It's good to know. And so the thing which was amazing with Stefan is that as soon as he has started his PhD, he became a star. So he was a star. So this paper was just extracted from Pour la Science. So Pour la Science, for those who are not French, is like a very general. It's not something that you can find in when you go to train station. So it's very general about science. And this article was already thinking that there is one guy, in Pennsylvania with applying wavelets, and he seems to be to go very well. And it was in '87, so I think he has started his PhD just 1 year before. And of course, as I said, so it's also something that we all benefit from the Yves Meyer. Extremely amazing teaching. So he was professor at that time at École Polytechnique. So he was delivering a course on distribution theory. So it was part of the course which was originally given by Schwartz, and he was very inspired. So and I know that Stefan benefited a lot from this interaction with Yves. And Yves is, when you know him, he's very generous, as you said. And something which is very amazing with Yves is that he can be interested by anything. So it's like you go in any audience, he will try to understand what happens and ask questions. Okay, so what I will describe today is something. So I knew that Stefan is a bit new in Monte Carlo. So I say, okay, I will just explain what we are doing there. So I do a lot of things in generative model, generative AI. And so I've chosen one of the topics on which I'm working on. And so I will start with what I call the machine learning tapas. So it's based on two papers, in fact, that have been written. One is written by Turner from NVIDIA. So he's a very good guy called Metropolis Hastings Generative Adversarial Networks. And the second one is papers written by very famous people. Charles Dickstein, he's a genius. He's one of the inventors of score-based diffusion model. It was mentioned this morning. So Hugo Larochelle and Yoshua Bengio. And I was amazed because these guys were doing Metropolis Hastings. So I knew Yoshua for quite a while also because he was a postdoc where I was when he was a postdoc when I did my PhD in Lannion, so a long time ago, so I know him very well. And he's quite good in simulation. He has this kind of culture. But I was more surprised to see people from NVIDIA. And when I read this paper, ICML, they did things which were very, very naive in terms of simulation. So I say, okay, perhaps a good idea. I did Monte Carlo for years. I can do something a bit better. It was not completely successful, but at least it was a try. So it started to. So the idea there was to start with GAN. So GAN is, as a way, so one of the many generative models which have been proposed so far. So not necessarily the most successful today, because it seems that diffusion-based model takes the power, and now it's consistency. So diffusion is already a bit old. So it's like a consistency models, which are it seems to be more fancy. But so GAN is a generation before, but it's already quite good. And GAN's goal is to generate fictitious observation for target distribution, of course, starting from samples. So there is a range of problems which are there. So when you do machine learning, so its dimensions are very large, the distribution can be quite complex, so you cannot do any kind of classical parametric modeling. And of course, you cannot do non-parametric estimation techniques are not an option. And so GAN, GAN is very original. I think it's a bit oversold, but it's very original in the sense that it uses a kind of adversarial schemes, which involves, in fact, two components. One which is called a generator, and the other is a discriminator. So you learn two things. So basically, you learn the generator. Generator is a way simply to produce an image, for example, or data from a latent space. So it's a function from a latent dimension, D. So small d is a latent dimension, big D is a image dimension, and G is typically a deep net, which has spatial structure, so with conv layer, but also flows and things like that. And then the discriminator is also a deep net, and this discriminator try to separate the true image, so which are in the observation space, a real example from fake examples. So as I say, in GAN, G and D are deep neural networks. So with the experiment I've done, I used simple GANs like spectral GANs or DC GAN. But of course, there are GANs which are much more fancy today and which produce much better images. But this is not affordable for our poor academics. We don't have the computing power to learn this very, very big model. So I will give example on simple GAN example. So what was observed by Turner and Bengio and Scholl-Dickstein is that you can do a better. Of course you can use a generator, but you can do a little bit better because you have learned two things. So you have learned a generator and discriminator. So basically that's the GAN training objective. So what you do is it's a saddle point problem. It's min-max. Okay. So what you do is you take this. So xi are the data. For the trained set, Zi are G of Zi are the data which are generated, D is a discriminator, and you simply solve this min-max problem. So you take the supremum over the set of discriminator, okay, and then you minimize with respect to the set of generator. So So at the end of the day, so imagine, so it's very, very unstable, it's very difficult to train, so that's another issues. But imagine that you can solve this type of min-max problem, which is a zero-sum gain. What you will obtain, in fact, you will obtain some density, so P of the data density of P of G. So PD is a density, if you wish, of the observation. PG is the observation is a density which is a push forward of P0, which is a distribution in the latent space by the generator G. Okay, and if you assuming that you have obtained the optimal discriminator. The optimal discriminator will be the Bayesian one. So it's optimal discriminator should be assuming that there are densities, of course. So there are many things that can be improved there. But assuming that you have density in the observation space, the optimal discriminator is equal to PD divided by PD plus PG. Okay. So what you can do, of course, starting from that, you can say, okay, so if I know how to generate PG. And I know also D star of X, which is a discriminator which has been learned during the optimization process, which means that if you simply identify what is a Bayesian optimal discriminator, okay, you say, okay, that you get a better approximation of the density for PD, for the observation, which is a product of discriminator, the generator distribution, so which is normally you approximate in PG is an approximation of PD, and then you multiply it by the exponential of D star of X. Okay, so it's a kind of energy-based model. So written there in the observation space. So you have to sample basically a distribution which is equal to the product of the generator distribution, which is easy to sample because the generator distribution is simply you take Z, the latent space, and then you apply the generator function G, and then you add some noise in order to have a distribution in the observation space, and then you remultiply it by the exponential of D of X. Okay, and of course it's not up to normalizing constant because it's a density. So that was observed in the Turner paper, and what he did basically he was using simple independence metropolis hashing. So what he was doing, he was proposing according to the generator, and then he was accepting or rejecting according to the metropolis hashing using, in fact, the exponential of the discriminator. Okay, so you can reformulate the problem, but not on the observation space, but in the latent space. So of course the latent space is of much smaller dimension, so in terms of sampling it's preferable. And in that case, so this is what was done by Chen, Scholl-Dickstein, La Rochelle, and these guys. And in such case, you can rewrite everything in the latent space. In the latent space, in fact, what you have to sample is PD star of Z, which is P0 of Z, so simply the distribution, the prior distribution on the latent space multiplied by this function which combine the discriminator and the generator. Okay, and they do this basically using a kind of Langevin-based algorithm. I will explain a little bit more later. So there have been many. So for those, because they are experts in this room on density estimation. So there is a lot of work which have been done recently. So in particular by Bio and Tanelian, but also many others, and myself also. So with students, and so we have tried to look at what does it mean to estimate. In terms of density estimations, what GANs are doing. So in fact, what you prove is something which is a bit not very surprising, but you can prove that after a lot of work, you can prove that you can do minimax, you obtain minimax. So in the classical smoothness class for density estimation over a compact set, you obtain a minimax estimation.
Just a quick question.
Yep.
So the logic of B on G effectively is the score function?
It's a kind of score function, yeah. Mm.
Okay.
Okay, so what we've done? So we start to look at one technique which is based on importance sampling, and that's for the exploration part. So I will explain a bit the samplers that we have used. So what it is based, the samplers that we have used is based on what is called importance sampling. So it's a very simple idea, so which is everywhere in computational statistics. So assuming that you have to sample from some distribution pi, what you do typically is that you will choose a kind of a proposal distribution, W of x, lambda of x. So lambda will be the proposal distribution, and of course the proposal distribution is not equal to the target distribution. So the target distribution, which is known typically up to a normalizing constant, and you denote by W tilde of x the importance weight. Okay. And the classical technique to sample or to estimate this type of function is you do the following thing. So you take a sample from the proposal distribution, it's xi, and then you compute the normalized weights, okay, which are given there. So it's self-normalized in the sense that the weight you don't have to know the normalizing the importance weight. You have to know the importance weight up to a normalizing constant because you use ratios there, and you simply compute this form. So it's importance sampling is everywhere. Self-normalized version of importance sampling is everywhere. Okay, it is biased, of course, because it's not, even if you take n large, you never really reproduce target distribution pi. But there is a trick, in fact, which is called iterated SIR, which I like a lot, and so I worked a lot on this trick. And the technique is as follows. It's very, very simple, and it's easy to understand, by the way. But what you do is that you do this technique, but iteratively. So you make a Markov chain which works like that. So you have a current state YG, okay. And instead of taking a sample of size n, what you do is that you take the first sample is the last sample YG, okay, so that you take it as a first sample, and then you draw independently n-1 sample from the proposal distribution, okay? So at every time you get, so you iterate, so you keep one sample, you just, this is, for example, the first one, then you draw independently n-1 sample from the proposal distribution, then you compute the normalizing weight, okay, and then you choose among this list of proposals, you choose according to this distribution, so which is a categorical distribution computed from the normalizing weight. You keep one sample, which is YG plus 1, and you iterate. Okay? And the thing which is perhaps a bit surprising, so we don't have to have much time, so is that the target distribution pi is converges, the target distribution pi is stationary distribution for this Markov chain. So obviously it's a Markov chain. And it converges to this target distribution when you iterate, whatever regardless of the initial distribution. It has been observed in a very, very beautiful paper by Chemeland, so which is, unfortunately this paper has never been published, I don't know why, but it's still on archive, many citations. And you can do many things with that. So you can do bias reduction. You can do self-normalized importance sampling. So we had a paper with students. You can apply this to do to state space model. So because this is the idea, if you are a bit so when you do particle Gibbs, particle filter, there is technique called particle Gibbs. Particle Gibbs is a special instance of this idea, and you can couple that variance reduction techniques and things like this. Okay, so we have several papers on this topic. Okay, so very, very simple idea. So a proof, I will not describe the proof, but it's a very easy one. So if you are interested, you can look at that. And so this algorithm is called EASIR, so it's iterated sampling importance resampling. Okay, and you can prove that this it has a very, very simple property. So this provided that the importance weights are bounded, of course, then this sample is geometrically ergodic, it's uniformly geometrically ergodic, okay, and it's very easy to relate its mixing time, okay, with this ratio, which is the ratio of n, okay, n is the number of proposals that you do at each step, and L, which is in fact the norm of the importance weights. So it's a bit misleading in the sense that, well, that's very, very general, but when you look at this quantity, of course, this importance weight, if you have a density which are defined as ratio, so which means that this quantity will grow exponentially with the dimension. So typically, it's okay, it's geometrically ergodic, but typically it will be this mixing time will depend exponentially on the dimension. Okay. So this is why, in fact, we use this kernel, but we use this kernel and we couple this kernel with kernels which are known to have much better dependence in the dimension, at least when the proposal distribution is log concave in the tail. And this we couple that. So we just use EASIR as a kernel to make a proposal in which introduce some diversity, and we use a local exploration kernel, which I call a rejuvenation kernel, locally, and I use as a default kernel, but you can do with something else. But we use iteration of what is called the Metropolis adjusted Langevin algorithm. Okay, but you can use also Hamiltonian techniques or no U-turn. So it's also possible, but we do all the theories based on Mala. So what is Mala? So you start with when Mala is based on what is called overdamped Langevin diffusion. So when you have an overdamped Langevin diffusion, so you look at an SDE which is given there. So you have the gradient of log pi. So you have the score there. So it's linked is the same diffusion which is used when you do score-based diffusion. So it's also a Langevin diffusion. And what you do there, you add some BT or the Brownian motion, and there is a very well-known result which says that this SDE is ergodic. Okay, so it converts this to it has a unique invariant distribution, and the invariant distribution is equal to pi. And the thing which is incredible, it has been observed by Langevin in the 20s, so even when the theory of SDE was not really there, so but he has the right intuition. So when what you call an adjusted Langevin algorithm, it's a kind of some type of discretization of the Langevin. So you discretize the Langevin diffusion. So the simplest discretization is Euler-Maruyama discretization, of course. But of course, there are better semi-explicit discretization, and in fact, when you apply this type of technique, it's safer to use better discretization. And what you call Mala, so it's called Metropolis adjusted Langevin. What you call Mala, which is one of the workhorse of computational statistics and machine learning and sampling in general. What you do is that you use EULA, you use an unadjusted Langevin algorithm, and you add some accept-reject step in order to correct from the gradient, from the error. Okay. And then at the end of the day, we obtain what we call our explore-exploit MCMC, where at every iteration, what we do, we do some exploration. Exploration is EASIR style of exploration. So we keep the original image, we keep the original sample, we draw a proposal, okay? We compute importance weight, we select amongst these proposals according to this importance weights, normalized importance weights, and then what we do is that, contrary to the explore-only technique, we apply, in fact, several steps of Mala algorithm. And we can prove a lot of things with this result under very general assumption, as if you assume that the rejuvenation kernel has nice properties, so if it satisfies the Forster-Lyapunov type condition, and it satisfies locally at least, so which is something which is much more reasonable, this type of bounds, then you can prove that the resulting result is a resulting technique. So the rejuvenation kernel itself is V uniformly geometrically ergodic. So we have a paper. It's very difficult to prove, by the way. So if you are interested, and it's only for the aficionados. If you don't have, so for those which are difficult to sleep, a lot of calculation to prove that, very difficult. So it's very, the funny thing is that it's very easy to prove that the SD is nice, it's okay. That's very, very easy, that the SD is geometrically ergodic. So when you go to the discretization without the correction step, it's also easy, but the thing which is difficult there to prove that you keep the geometric ergodicity is the accept-reject ratio. So in fact, it was like a conjecture that it works in practice, but in fact, it's difficult to understand. You need to have some condition, and it's not so easy to prove that the geometric convergence of the diffusion is not spoiled by the accept-reject mechanism. And then, starting from that, we had a kind of magic kernel. So, okay, it's a bit difficult to read, so especially for a birthday party. But so which proves that you get good results, so which is without geometric. Of course, you have the dependence in the dimension. Now people are very interested in by dependence in dimension. So this type of result is obtained using classical Markov chain Markov chain techniques, so which are based on regeneration ideas. But there are other analyses which have been developed more recently using conductance arguments, so more from people from CS, from computer science, using isoperimetry or Chigger's inequality. You can use also more handcrafted coupling techniques to prove, in fact, that you have dimensional dependence which are more or less polynomial in the dimension. So it's like, this is the type of result that you can obtain, but not necessarily with this type of techniques. Okay, so we have this type of exploit. I will just give you some examples. So when you do a sampler, it's always safer to look at very, very simple problem first. So when this is a very simple Gaussian, so you have a mixture of three Gaussian distribution. You are in small dimension. And even in this dimension, it's incredible. The Mala sampler is completely stuck in one mode. So it's called, which is, okay, understandable because the probability of crossing from this point to this point is very small. When you apply I0 in this dimension, it works quite well, but you draw at random points. So of course you don't explore really well the mode. And when you do this explore-exploit algorithm, it works quite well because he has, so the I0 helps to draw points outside, so you escape the local mode. And the dimension is not too large, so it's still okay. You find other modes, and then because you apply this local kernel, the local kernel explore correctly all the modes. So it works well, and you can see that here. So it's very impressive. If you look at the forward KL, or if you look at the total variation distance, you can see that. So I see the Mala is doing very, very badly. So it's funny because Mala is stuck in one mode. So it's TV. So we are in dimension 2 and look at the TV. It's still very so after 35 steps we are still at very high level. So because he missed a mode basically, whereas X2 MCMC is doing very well. Same thing. So number trajectory forward KL and okay. So it works quite well. Okay, so we can do adaptive stuff, so we not explain. What you do typically to improve proposal is a technique which is called neural importance sampling. And in neural importance sampling, what you do is that you use you have a proposal distribution, and you apply on the proposal distribution you put a normalizing flow, and there are many very good flows. So it's a technique to shape distribution with it's a way to parameterize diffeomorphism with deep nets, if you wish. And then starting from that, there are many techniques to adapt this flow. So you can do neural transport, neutral MCMC. So there are many ideas to to apply that, but the way we apply this, in fact, is that we make better proposal, and you can do, instead of proposing according, for example, to P0Z, we can propose to according to other distribution, and you solve, you adapt, in fact, this proposal by minimizing, in fact, a kind of evidence lower bound, which is obtained by combining forward and backward Kullback-Leibler divergence with respect to the distribution pi. Okay, so you solve, it's a kind of adaptive MCMC in the sense that you mix sampling techniques with an optimization techniques, and it works quite well. So I worked a lot on this type of ideas. So it's the new thing is to use this type of flows, okay, and you obtain what is called flex2, and it works very well, even on very challenging geometry, like this one is called the funnel technique. So when you look at the Radford-Mead funnel, which is known to be extremely complex because it has very complex geometry, so the dimension is 100 there. And so of course we project in 2 dimensions, but the dimension is large. So you see that flex2 is learning quite well the distribution, whereas the gradients are just enormous, whereas the corresponding technique which has been developed by Andrew Gell-Mann and all these co-authors of Mart Hoffman and from Google, Nuts is stuck. In fact, he has problem to both in both sides. Okay, because the way they adapt their gradient is not so it's very homogeneous in terms of gradients, and it is not able to capture this stuff. Okay, image. So okay, we do better. It's not very impressive. So now one application. So it's with MNIST. So MNIST is very easy. So we use very simple GAN for MNIST. Everything works for GAN. So that's more or less distribution. So it's in dimension 2. So in fact, the latent space for MNIST is 2. It's only 2. And that's the posterior distribution. So it's that's the distribution that we are willing to sample. Okay, the distribution, once you take into account the generator and the discriminator, this is, and in red you have the point that you have obtained using ICER, okay, and you see that ICER is missing, so it doesn't move very well because he has a problem to move between modes. Mala is only local, so Mala doesn't move too much because it's very, very local, and X2 MCMC works quite well in this case, and this is clear there, so it's like, this is, you see there the generation, and you start from an 8, so you look, and then you become the 0, 1, 6. So you are really sampling. Whereas if you look at NIST, and this is what the technique basically that was done by Turner. In fact, you don't move much. Okay, so you don't move at first because you are stuck more or less in one point. So our technique on NIST works very well. We have also technique which so it works also well for more complex models. So it's based on CIFAR 100. And we use not a very fancy GAN, it's called DC GAN, so it's a deep convolution GAN, so it's from the 16, so it's like grandpa of GAN, so nobody uses DC GAN now, but it's the dimension is, okay, so it's 100, that's projection there, and this is typically the type of result that we obtain, so it's a type of result, so if now that you are used to DAL-E, so it's not very, very good, but it's because its models are not very large. Okay, so you can prove that it improves. So you can see that it's even better. It's even better to look at what it does. So you see that our technique Flex2 works very well in terms of that's the energy. SN GAN, so spectral GAN, so works also quite well. So for the energy profile. So what you see there is that this technique improves the energy. So if you interpret the GAN as energy model, in fact the sampling find better energy. So there is a phenomenon which has not really been observed, or I think which has been observed by people, is that when you look now at the typical quantity which are looked by people which are doing generative model, like inception score or Fréchet inception distance, in fact it starts to improve, okay, quite significantly. So you gain 10, okay, and then it starts to re-increase. So it's something I did not have time, so otherwise I could explain. So which means that it seems that in fact the sampling with this type of technique improves the quality of images, which is true, by the way. And that up to some points, when you look at the Frechet inception distance, it starts to degrade, whereas the energy is always increasing. So it means that you produce images which are perceived to have quality which is less good, whereas the energy seems to be better. And in fact, this is because typically you start to look at points in the discriminator which are badly trained, okay, and will correspond to kind of. So you need to regularize. So which means that you need to regularize the discriminator to avoid this. So okay, that's another talk, and that's it. I think I thanks everyone. That's the paper, and thanks for your attention. So you have not the age to ask for a PhD there, nor postdoc, I'm afraid.
Just a quick question. In the popular diffusion methods, we rarely see rejection treatment, MALA, but we do see a lot of annealing.
Yeah, I did annealing also.
So annealing would be a replacement for the rejection concept of Metropolis?
No. No, annealing is more like a flow. So in fact, it's like a flow based. So it's like annealing is more like you have a continuous temperature, and you can do important sampling with annealing, so which is a classical technique. It's called annealed important sampling. So it's a very, very classical technique. I think it's the most classical method to compute free energy or normalizing constant. So it's Alzire with an annealing in temperature. But no, it's not really. We can discuss later on, but it's a different technique. Yeah, it's more flow based. So flow based is more like the idea of diffusion is more like you use a diffusion to you have a Fokker-Planck behind that to transform and then you try to discretize the Fokker-Planck. So it's more like all this flow based idea. No, I think Metropolis is not at all like that. No.
Two quick questions, one from Rich and one from Amit. You can go first, Rich.
Super quick. Did you name your method Mala in honor?
Without a T, but exactly.
Now, my question didn't have to do with Stefan, but of course I didn't follow all the technical details, but the GAN is inherently unstable. Okay, you have a one-to-many map. It's inherently, your Jacobian is going to kill you. So what's going on?
So there are two things. So that's stamping GAN. So you take a GAN which is already sampled. Okay, so you have a GAN which has already been learned. So there are two problems. So you can learn GANs. Okay, you have to solve the saddle point problem, and of course there is a lot of tricks. And then once you have a GAN, you have two things. You get a generator and a discriminator. So either you use simply the generator, okay, and so everything that you have learned from the discriminator is lost, or you use at the same time the generator and the discriminator. So what you do basically, you do an energy-based model using the generator and discriminator. And what has been observed by people, is the paper MCMC GAN, is quite popular by the way, is that it improves, and something which is strange somehow, is that these people never report that the Fisher inscription distance was decreasing initially and then re-increased, okay? And it's clear. And you can take the best GAN model, you will always observe that, okay? So which means that there are some problems in the discriminator, by the way. So now for the learning step, you can prove results, okay? So you can prove results on assuming compact support and things like that to avoid all this. When you do density estimation with compact support, ConvNet, you can prove that it works. The thing which is normal somehow is that it does not do better for, say, Sobolev class for density on compact support, and with Sobolev type of for older class of regularity, you don't do better than classical estimation technique. So the thing which is strange is that why GANs? So that's a good question. So why GAN compared to other density estimation method? No, older class so why GAN for this type of technique? That's a true question. But otherwise, no, it's quite well understood by the way.
with these open questions, we're going to thank Eric again.
Thanks a lot.